This question is related to wave. The radio station uses a frequency 693 kilohertz for broadcast. Explain how it is possible to receive this broadcast on other side of a hill of a radio station. So this is about the diffraction of the wave. So when we use a frequency like 693 kilohertz is there, so we can work out the wavelength first to understand like what will be the wavelength, because the longer wavelength, greater the wavelength is great. If the wavelength is longer or greater, it will diffract more than the shorter wavelength. So the radio waves are there. So first we'll work out the frequency, appropriate calculation. So first V equals F lambda, or lambda is equals to V divided by F. So V is speed of the wave, which is 300 million meters. So 3 exponent 8. So the speed of the wave is 3 into 10 to the power 8, and the frequency is 693 kilohertz. That is 693 into 10 to the power 3. When we divide these two, we'll get the wavelength which is produced. It is 433 meters. So that is a very long wavelength. So how we are able to receive the signals from this? Because compared to the size of the building, the wavelength is longer. So longer wavelength diffract more. So if anyone is a house is there surrounded by a tall or a large building, can receive that radiation. So longer wavelength diffract more. The second part, the radiation flux of radio waves arriving at a particular house is, so we have watt per meter square flux is there. The formula which relate the radiation flux is power per unit area. So P divided by A. Calculate the energy arrive at a person head from these radio waves in 1 hour. Area of the head is 0.025. So first we have the power, we have the area. We'll first, we have the flux and we have the area. We'll find how much power is there. And from the power, after finding the power, we'll have the formula. Power is energy divided by time. So energy is power multiplied by time. So basically we want to find how much energy is received by the head in 1 hour. And remember, time should always be in seconds. So it will be 60 into 60. So 3,600 seconds will be there. So first we'll find the flux. First we find the power. The flux is power per unit area. So flux is given, which is 8.3 into 10 to the power minus 9. So this one is 8.3 into 10 to the power minus 9. Power we don't know. And what about area? That is the area of the head, 0.025. Multiply. This will give us the power. So that will be 8.3 into 10 to the power minus 9 times 0.025. That will be P. And the energy which we receive in 1 hour, that is power multiplied by time. So we have the power, which is 8.3 into 10 to the power minus 3 times or multiplied by 0.025 multiplied by 3,600. So when we multiply all these factors, the energy which we receive in 1 hour, that is 7.5 into 10 to the power minus 7 joules. The continuation, this is part C. For the question, a student makes the following comment about the answer to part B. Although this electromagnetic wave is a very small, the energy, electromagnetic wave energy is very small value and safe. Same amount of electromagnetic energy at an ultraviolet frequency could be dangerous. Comment on this. So here, the last answer, when we calculated the energy of a radio wave, which was 7.5 into 10 to the power minus 7. So ultraviolet, what will have? Ultraviolet will have a high frequency. If it's having a high frequency, it means it will have a high energy of a photon. And high energy photon can cause ionization. So here, remember, we have the formula E is equals to HF. So if we are using an ultraviolet, it will have a high frequency. High frequency means it will have a greater energy, or the photon which is associated with ultraviolet light. So ultraviolet light will have a greater frequency. When it will have a greater frequency, it will have produce high energy photon. And as a result, when it will produce high energy photon, what is the effect of high energy photon? It can cause ionization. So yes, it will be dangerous. That's why for communication, we are using a radio waves.